I'm going to introduce Professor Bob Norwood. I guess it's the College of Optics, technically. And a little tidbit, I have known Bob for my entire time I have been at the University of Arizona, which is pushing 17 years. Including he let me audit his class when I was a postdoc. So I've known Bob as a collaborator, as a PI in a center, and from the professor's side, and generally a very exciting area of research that he's going to be telling you about today. So with that, I'm going to let Bob go ahead and take it away.
Thanks, Aaron. We were in a big NSF center together, as I recall, and we first started working together. And you were still a graduate student, then the EFRC, and so forth. So yes, I was asked to present on polymer integrated photonics, and there's definitely going to be integrated photonics and polymers throughout the talk. And then there'll be some things that are more just integrated photonics and some things that are more just polymers. And overall, we have this internet, which is ultimately an optical network. And I'm going to talk about some things that are really kind of more used for cameras and imaging, but what's going over that optical network? Why do we need this giant internet? Because you guys are all sending pictures all the time and videos and things like that, right? So and that's optical too. So we're just totally driven by optics these days. Fifth, we're now the Wyant College of Optical Sciences because of the great benefactor James Wyant, who's basically donated $30 million to our college over the last 10 years, and I'm also a faculty in field science. So this is an old picture, as many of you can tell, because the big new building is not there yet, but the big new building is going to open, I think, in about 3 months. We're going to be very happy when it does, because it's very loud all the time, and we can't even get to our cars anymore. But that's where we are, and they literally are closing the pathway between the building and the Chevy garage next week, and we haven't been able to do it. Now we can't. I don't know what we do. Just don't come to work, I guess. but that's where I sit. So when you walk past, and sometimes you'll see me there. I gotta get rid of this business. I'm not sure how I do that. Get my mouse in someplace. How do I go with this? Okay, there we go. Okay, so at the bottom line here, and the reason I'm here talking to you is the internet. I got involved in optics and photonics before there was an internet, when fiber optics was just being used to carry phone calls, and that was all it did. And now it carries all manner of information, and increasingly it does all of that within buildings like this. So if you look at the growth of the internet right now, most of it's inside data centers. It's not between you and somebody in Australia. It's all of the computing and other things that are going on inside data centers. So anybody know what an exabyte is? How much is an exabyte? How many zeros? 18. So it's 10 to the 18th. And so you can see 400 exabytes. This year we're going to hit zettabytes. Zetta is 10 to the 21st. And by the end of the decade, we'll hit yottabytes, which is my favorite, because like a whole yottabytes in 10 to the 24th. Bytes per month that is going over the internet, and a lot of that is happening in these data centers, which have increasing needs to use photonics at a smaller and smaller and smaller scale. So photonics always wins when you want to send information. It's a product of the information's bandwidth and the distance. When that product gets large, you usually go to photonics. So what is photonics anyway? Optical photonics are a science application. This is from the Harnessing Light, basically monograph that was created by a bunch of National Academy members about 10 years ago to look at the future of photonics. So optics and photonics are a science application of light. Photonics in particular concerns the generation, control, and detection of particles of light for advanced manufacturing, robotics, medical imaging, displays, defense, and many other areas. So these still are the primary areas in photonics. Of course, the particle nature of light was initially hypothesized. Well, it could have been before Newton. Newton hypothesized that, and then everyone said Newton was wrong about that. The only thing he was wrong about that. Later, it turned out he was right about that, like everything else. And then basically, this is what we're doing with photonics, and we'll continue to do with photonics is to try and increase everybody's quality of life. So a lot of photonics is consumed, and when I say to me, it's impossible to think about photonics without optical fiber. And fiber is it's an optical guided wave. So what is guided wave optics? And if you walk down a couple of blocks, there's the Tyndall garage and Tyndall Street, and Tyndall was an actual person, who was a very successful scientist in the early 1800s, and Tyndall basically first demonstrated total internal reflection, which is what makes optical fiber and the internet possible. And he did this using water. There's Tyndall. Water has a higher refractive index than air, so light can be trapped in it by total internal reflection. And basically, any optical waveguide is any sort of conduit that works by total internal reflection. It can be a slab of material, it can be a liquid, it can be layers of material, which is primarily what we'll be talking about today. And by far the most widely used waveguide is optical fiber. Two concentric cylinders, you can think of it that way, of low loss dielectric material. There's glass. Now, I don't know if this is going to work. And I don't know if I really want to deal with the sound aspect. Oops. Okay, so let's see if this works real quick. So I can check it. Yeah, so I don't think we'll hear anything. That's okay. So you can see what this guy is doing. He's got he's shooting a green laser through a tube of water that has a hole in it, and and the light is being guided in this spout of water by. So this is basically a form of the Tyndall box, and the amazing thing about total internal reflection is that if you have a perfect interface, there's no loss of light, and every mirror you've ever used has some loss of light, no matter how good the mirror is. You might say, why don't we just put gold along a piece of glass? Will that work? It won't work. Very quickly the light will attenuate because the gold absorbs a little bit of light every time the light bounces off of it. So that's a real live demonstration of that effect. And waveguides come in all shapes and forms. For much of our work today, we'll be talking about waveguides that are quite small. Silicon photonics, which is incumbent leading integrated photonic technology. The waveguides are 400 nanometers wide by about 200 nanometers tall. When you bend a fiber, light comes out because you frustrate that total internal reflection condition. This is a nice picture, actually, of waveguiding in a cylindrical piece of glass. Also shows the sort of evanescent field effects. So there's all sorts of ways we see waveguides every day. So waveguide geometries. This is a very common starting waveguide geometry called a slab waveguide, where we have a higher refractive index material surrounded by two lower refractive index cladding materials. This is more what an optical fiber looks like, except an optical fiber is cylindrical. We'll look more closely at that in a moment. This is the format of most waveguides that are used in integrated photonics. So it's a rectangular or square core surrounded by a common cladding material. So it's generally advantageous to have the cladding be the same everywhere, because then the waveguide is less polarization sensitive. And one of the things we're constantly dealing with is the polarization sensitivity of waveguide devices, because even when you do this, there's still some polarization sensitivity, and that limits how they can be used in some cases. And in some cases, it's an advantage. Sometimes you want that polarization, but it's relatively few number of cases where that's the case. And then, this is a scale picture of an optical fiber. So that's how small the core is. So this is why our graduate students take so long to get out of grad school, because they have to match up this core is 8 microns wide. So you have to get two, many times you have to get 1 or 2 of those matched up to within a fraction of a micron in order to get enough light going through to actually do anything. So that's one of the realities of optical fiber is that it's still a challenge to package, and improving the packaging capability of photonics is a very active area of research today. So, I call it hairy glass because it's about the same diameter as human hair, optical fiber, and it has a core, and the doping is very modest. So the glass cladding is fused silica. It's SiO2. It is all of this is generally made for the commodity fiber that we use every day, which is SiO2 in the glass cladding and germanium doped SiO2 in the core. It's created by a vapor deposition process into a preform initially, so that it uses ultra pure starting material. Initially, when people made glass fibers, that maybe look like this, they had no chance to actually enable the internet because the losses were too high, and they were mainly too high because of impurities that were present in the starting materials. The processes was developed at Corning and Bell Labs and other places in the early 1970s, wound up making optical fiber a reality. So again, this is the array picture. We won't get too much into talking about the wave and the electromagnetic treatment of this, which we have entire courses on if you want to take them. But this is basically what you're talking about. You have to hit the interface at the critical angle for total internal reflection. And there's our nice tube again. And you might think about this, well, Dave, I've got this piece of glass that's the size of human hair. It's probably going to be pretty fragile. It is pretty fragile. So another challenge of optical fiber research is dealing with the fiber, because it breaks if you aren't careful. And there are various tools that we have to cleave them, to fuse them together, to position them. And but any actual optical fiber that you would buy will generally come with some kind of packaging around it. It'll have a polymer cladding. It might have a buffer that's made of a very strong material. It could have a jacket made of kind of a heat shrink type material. The buffer material sometimes are as strong as Kevlar, depending on what the application is. So, and that's all to basically make it so you can handle the fiber. So this is basically the world of optical fiber in terms of the wavelengths that we generally work at on the internet. So dB units. A dB, is generally mostly associated with audio units. So but 3 dB is about a factor of 2. 10 dB is a factor of 10. It's a logarithmic unit. It's 10 times the base 10 logarithm of the ratio of the input to the output. You can see that for optical fiber, for optical fiber, there's a minimum at about 1550 nanometers in the loss. The loss in this direction, this increase is Rayleigh scattering, same thing that makes the sky blue. This big peak here is water. When you make silica, you always have a little bit of SiOH left over, and that SiOH, the OH, gives you this water, what's so-called water peak, you get and you can get rid of it, but it's not really worth it usually. And this magical place here, the C band and to some extent the L band, is where 1550 nanometer light is, and that's special because again the loss is very low, 0.2 dB per kilometer. Just to kind of put that in perspective, if we go from here to my house, which is about 20 kilometers away, then that's about 4 dB. So it'd still be almost half the light would make it to my house, 4 miles away. There's no material you've ever seen or ever see other than optical fiber that can do that, other than a vacuum. It's incredibly transparent. The red region is called the C band because it's a conventional band for optical amplification. So, and what that allows us to do is not just send one signal along optical fiber, but send many, many signals along the same optical fiber through a process called wavelength division multiplexing. And that's really what enabled the internet, was low-cost optical amplifiers that enabled signals to be boosted up without the need to turn them back into electrical signals. Because if you need to do that, it's very costly. And sending multiple wavelengths down a fiber is kind of pointless, because they just have to put a whole bunch of electrical to optical converters every 20 to 30 miles or so. So you can go long distances. You can also go to very high speeds. When the internet started, twisted pair phone cables was what most people had coming to their house, and they might have had in the U.S. you might have had coaxial cable from your cable company. In most parts of the world, you only had this, because cable is a more or less uniquely U.S. phenomenon. And that had a carrier frequency, which is basically your bandwidth, of about 50 kilobits per second. Hard to imagine, but brilliant engineers, some of them in Tucson, a company called it's escaping me now, but it was a big chip company in Tucson, came up with something called the DSL chip that made it possible to send very high bitrate signals along those little copper pairs. That'll come to me. But most of us still get the internet over coaxial cable from our cable company, whether it's Cox or Comcast. And it's a simple reason. You can see it's a factor of 1,000. The cable companies, if you were in the industry and you saw this happening in 1995, as I did, it was kind of a no-brainer. I mean, the cable was going to win. It's just a question of time, because physics always wins if you just wait long enough. Sometimes engineering gets around it for a while, but eventually physics wins. You know, and now we've got wireless, you know, wireless obviously is great from a carrier frequency point of view, but it has limited distance, and it has, you know, other problems with respect to obstructions and line of sight. And an optical fiber is way up here, so you can see why at the end of the day we're not going to be getting rid of optical fiber anytime soon. And this is the other thing is, you know, this is this wavelength division multiplexing. So not only do we have this high carrier frequency, and this is I actually cobbled together the Dark Side of the Moon album for fun, made it look like wavelength division multiplexing. You know, that's what we do. We take multiple wavelengths, we put them into what amounts to a prism. It's a multiplexer. We put all that down a single fiber. Then on the other end, we have another prism which rips out all the different wavelengths, and they all have separate information on them. And that's WDM right there. Okay, so now we're going to get into really integrated photonics, and I'm going to jump right ahead. I'm going to show you why integrated photonics is useful in a minute, but I'm going to basically say, you know, if it involves silicon, it's probably good, right? I mean, our entire world is enabled by Moore's law at this point. And about 40 years ago, it actually came out of the DoD. A guy named Richard Soroff had the idea that silicon would be good for photonics, you know. And it seems dumb because you can't really make lenses out of it. It's this crystalline thing. It's opaque and invisible, but it's actually great at these wavelengths I just talked about. It's transparent at 1550 and, you know, 1 to 2 microns. And you take advantage of everything people know about how to make things in silicon, but you're making them in for photonics instead of electronics, which in general makes things much easier. There are little details, like electronics doesn't care about roughness so much, but the photonics does a lot. You know, so because roughness scatters light and it makes our total internal reflection not work. But silicon's got a tremendously high refractive index, which is great. It's at 3.5 or so. It's transparent at the wavelengths we want. You can make really compact things. Those little rings there are each about 10 microns in diameter. And the light can go around them and pretty much not come out. It can bend it really tight because the index is so high. So my TIR condition is really satisfied because of a big difference in index. CMOS compatible, and that's not always a goal for photonics because the volumes aren't at a point yet where you really need to care about this in some cases, but it's more and more a consideration. Low cost material, and you know, there's some drawbacks, which part of what has happened over the last 10 years is a realization that you're not going to solve all the problems in silicon. You need to be able to put silicon together with other things, which creates some of these packaging packaging opportunities, because you can't make a laser in silicon, or people have tried lots of, you're not, it's an indirect bandgap semiconductor, which makes it basically impossible to make a laser in, and you can play games, but what people do have realized is, well, we can do a lot of other things with silicon. We'll just bond gallium arsenide or indium phosphide lasers to silicon, and that's in fact what people are doing. And you can't detect things either, but you can easily integrate germanium with silicon, so that's become the way to go, because germanium can detect things in this region. So we started working on this in basically about 10 years ago. We started working on silicon photonics and bringing other materials to silicon photonics. And at the time, we were focused on doing that with electro-optic polymers. There are still some groups doing that. We've moved away from that, but that was part of our goal, in addition to other what we call hybrid systems. At the time, we had these 5 university groups that were working with Sandia. So there was no place in the United States at the time to do what's called a MPW run to make silicon photonics. But we worked with a really good group of Sandia. They were very kind, provided us with design rules and taught us how to lay things out for silicon photonics. And they made these chips, and we did some nice research with them. That was part of what instigated people to look at major facilities, which we'll talk about in a few minutes. So I'll give you an initial example of what we did there. Okay, so why is this useful? So this is sort of inside of a telecommunications or optical communications networking building that's got all kinds of servers and equipment. And this is a piece of optical equipment. This is another piece of optical equipment. A variable optical attenuator just makes the light level up and down. The multiplexers and multiplexers are doing that prism stuff I showed. Electronic controls. This is a fancy switch, another fancy switch. And what integrated photonics does is, and you can see how big this is. It's big and bulky, it's heavy. You can basically, this chip, which is about 1 by a half a millimeter, has practically all the functions that all these boxes do on one chip. So that's the real value proposition. Now, can you make kind of less highly integrated things that are also valuable? Yes, and principally those are transceivers, which are really devices that put a signal on a fiber and take a signal off a fiber. And there's a lot of those now that are easily integrated with silicon and are all over those data centers I showed before. So over in optics, we have a NanoFab facility there. It's managed by Dr. Roland Himmelhuber, who actually got his Ph.D. In our group. And to be able to make these sorts of integrated photonics, you need to use, in general, some pretty advanced tools. This is an example of what we have there, both to make integrated photonic circuits, so things like e-beam evaporators and plasma etching, reactive ion etchers to etch out patterns. This is a lithographic system that allows us to make lithographic patterns without photomasks, which is a very nice capability. So we don't have to make photomasks anymore. So we just literally put our designs into this instrument, and it can pattern it in a photoresist, and we can transfer that pattern to the material of interest using systems like this one, and maybe this one doing well. Then we have packaging equipment that bonds wires to chips, can bond chips together, can pick and place chips. So that's all over in our optics building that I showed you before. And then, so that's on the kind of one part of the building. And then another part of the building, we have a testing area. So if you have photonic chips that are you have interest in testing, we have a very extensive capability to both do passive and active, what we call passive and active testing. And you need these piezo positioners because you've got these tiny fibers, and you've also got tiny chips, and you kind of get these things lined up to within fractions of a micron, and without going crazy. So we have nice instruments for doing that, for looking at the spectra of the fiber, you can see the fiber here and the chip. So microscopy and imaging systems and all that kind of stuff. And that's what you need in order to do this kind of work. So one of the early examples that we had is trying to pursue what's called athermal silicon photonics. And the idea is, here I have what's called an interferometric device, and there's a condition for a resonance. So these little rings are the purpose of this ring is to pull off one of those colors. So I got a stream of information coming down the fiber. I couple that into my chip, and now I want to pull off one of those wavelengths. This ring is resonant with one of those wavelengths, let's say lambda r. It pulls it off, and then there's another waveguide here that just drops it to a detector. Okay, so it's a demultiplexing element. Problem is it's temperature dependent. Silicon actually has a pretty high temperature dependence of its optical properties, and it also would have a tendency to expand or contract. Both of those things affect this resonant wavelength. So we actually looked at trying to make it so that it would be less sensitive to temperature, so you wouldn't have to control the temperature, because that's not a good thing for in most cases, and it's definitely not good in a power-consuming data center. So this is a sort of work that we would do to make that possible. This was our received chip. We took the top clouding off. This is a wet etch process. We've now developed a dry etch process for doing this, and then putting a top clouding layer on that would basically make the chip less temperature sensitive. And we did all that. We measured. This is actually these resonances. This would correspond to different wavelengths that I would be able to pull off that stream of wavelengths. And they're periodic, because it's like a cavity, like a laser cavity, has a periodic modes. This difference is called the free spectral range, and it actually worked. So we published this some time ago, but we're working on making this work a little bit better, because we had to kind of cheat a little bit in that we made the waveguides a little bit narrower than they ordinarily would be to get this to work, and we want to work with more standard waveguides, so we have an approach to that. And but you can see how flat this is. What the temperature dependence looks like if we take the chips that we got from Sandia. When we replace the top clouding with our tailored top clouding, we were able to get very flat behavior. So basically that color we were pulling off stayed the same over about 80 degrees. So and it continues to be an important problem in silicon photonics. Okay. As I said, we didn't have any way to make silicon photonics in this country. So that was a polymer basically we put on top of an organically modified solid gel. I'm not going to go into details of it. I'm going to say it was very similar to silica. This is AIM Photonics facility in Albany. So it's at SUNY Albany, and it's a large fab that was built initially for microelectronics. It's now purposed as well for photonics, and anybody in this room can now lay out an AIM chip and pay your money, which I haven't checked that because I haven't done a run in a couple of years, but it was about $25,000 for what they call I think they called it a mini run, but you still get, I think, 25 or 30 chips for that out of it. And that might sound like a lot of money, but we used to be, working for 5 years in the lab to make one of those chips. So it's really not that much money. It's much cheaper than working for one. I gave up after a while. You'll see that we still do our own stuff, but if you're doing silicon, it's kind of pointless to do it yourself now, unless there's something really special that you're doing, because these chips are so good and so reproducible. We recently published a paper on statistics, and they're just practically identical from chip to chip. So the polymer aspect of this problem for us was looking at connecting different chips. So I have a silicon chip here. I've got I want to get off the chip and get out to a fiber. Maybe I want to go on to a different kind of optical printed circuit board here. And so this is the big picture is I've got silicon chips that have light on them. I want to get them out in an easy way. It's almost like a printed circuit board type way. And do that with polymers. Use polymer waveguides to get off the silicon and then onto the fiber. So we did a lot of work, learning how to make AIM chips, learning how to characterize them. When you look at these chips, so this is a chip. I'll show you the device that's on the chip for a minute, but if you look, there's there's these regions. That's where you know, there are optical devices here, but they're very small. The rings I showed before you cannot see on this scale. And all of this stuff, all of these, when you see all of these bright squares, those are bonding pads. They're for the electrical part. They're to put electrical signal in or put another signal in to control the temperature. So much of the space on these chips is actually taken up by electrical elements because the optical waveguides in silicon, to keep them small enough that we don't have problems with what's called the different modes in the waveguide. So we generally work in what's called a single mode waveguide, so that we don't have multiple ways for the light to get through, because if there's multiple ways for light to get through, then the signal that we're sending can ultimately get distorted. So these are very small, they're 400 nanometers wide, you know, and these pads are, you know, 50 microns wide. You can't really see them on this scale. 220 nanometers. Yeah. And one of the challenges, you know, to go back to the gauge thermal stuff. So one of the reasons that people incorporate temperature control is the thickness control is actually one of the hardest parts. Because when you look at, if you look at the lithographic capability now, I mean, you can easily get, I mean, if it's 400 nanometers, I can get 400 nanometers plus or minus, you know, a nanometer, you know, if I'm good. But I can't do that as easily for the thickness. I mean, and it has more impact because it basically, the way you get thickness control is by chemical mechanical polishing. So you're like CMPing it down, like, okay, stop, you know. And if you're off by a couple of nanometers doing that, that's going to move your resonant wavelength around by, you know, essentially whatever the ratio is, because it's pretty much linear with it. So a 1% error there is a 1% error in that wavelength. That C-band is pretty small, so a couple of nanometers makes a difference. You're kind of cramming a lot of stuff in. So yeah, that's kind of the reality. Good question. So we developed actually interconnects materials, a new class of interconnect materials for this problem that we just published. We've published a couple of papers on this now as well. These are fluorinated materials. So, and the purpose here was we were trying to actually connect a silicon chip to a glass waveguide. The glass waveguide performing the function of an optical printed circuit board. And so we initially developed these materials. These are beautiful materials because they can be patterned for optical waveguides as a dry film. We don't have to do any develop step. We just have the film on a carrier film. We pattern it with light, and we literally make the circuits in situ. We can use that instrument that doesn't require a photomask to find the two waveguides we want to connect, and you literally stitch them together in real time. And we did that here. So after we developed materials, we showed that we could do this. So we could go and the chips we used here were actually glass chips. So you look here, there's chip A and chip B, and we've got a film that is carrying the waveguide material that I just showed you on a commercially available fluorinated polymer called Tefzel as the bottom cladding and the structural support. We basically laminate these films onto the chips. We look for the waveguides, then we write the waveguide that we want to connect the two chips with, and it worked pretty nicely. The next steps on this are a little bit bigger steps because we need to get to something for many of the applications, and people are really interested in this, but they want things that can survive a solder reflow packaging process, and that means you have to go to 260 degrees C for about a couple of minutes, maybe a couple of times. And there's not a whole lot of polymers that can do that. We are working on making these more thermally stable. But that's an example of what you need to do now to keep growing out these bandwidths is to connect different chips. And we've done that with a low loss polymer chip. This is I showed you some chips earlier, and this is actually a pure silicon chip, but it's just of interest to see what you can just get from off the shelf from Photonics. These are microdisc modulators. Each of these works at a slightly different wavelength in our prism, and these little dips. Each of these dips corresponds to a place I'm pulling off light. In this case, it's a modulator. So I'm actually purposely, I'm not going to go into the principle of how these work, but I can purposely make these little spectra move a little bit with an electric field. In the same way a photodiode works. I supply a current and it changes the optical properties of silicon a little bit. And when it does that, by the same token that temperature can move these resonances around, that little change in the optical properties can move the temperature, that around. So if I'm sitting at a wavelength and this guy starts moving, it's a modulator, and it can be a quite fast modulator. We made go into the details, but these were working up to 25 gigabits per second or so. So this one chip could have 100 gigabits per second on it, without too much trouble. And we actually did cryogenic work with that. Okay, now I'm shifting gears to not integrated photonics, but still polymer photonics, and but stuff that you need to actually keep the internet and Moore's law going. More imaging technology. So this is about really new materials that we've developed for infrared optics, and there is some integrated photonics in here too, of our own that I'll get to in a few minutes. But infrared optics has been occupied primarily by crystalline semiconductors that have heavy atoms like germanium, zinc selenide. Silicon itself is not bad. Chalcogenide glasses, which include things like arsenic and sulfur, but polymers not so much because of reasons we'll see shortly. So infrared absorption comes from nuclear motion. That's generally known. I mean, you can have very low bandgap semiconductors where it's still electronic absorption, but generally we're talking about oscillating nuclei and bond vibrations, and these correspond to various kinds of vibrational modes. This is a simple picture and animation that shows that. And what largely governs the frequencies at which these vibrations happen are the masses of the respective atoms and other factors that affect the intensity of the absorption. But the positions of the frequencies are relatively easy to predict in sort of a little bit beyond harmonic oscillator models. I just have a simple oscillator model here, but the important thing is to note that you care about this reduced mass, and that reduced mass becomes the mass of a small atom. If you have a small atom and a big atom, you can see that this basically becomes equal to the mass of the small atom, which makes this small atom mass, which makes this energy big, which makes you have absorption in the infrared at high energies. That's why anything with hydrogen in it, we saw that water peak in the fiber spectrum. Anything with hydrogen in it has absorption in the infrared. So we started working on these materials about 10 years ago. It's interesting that I just changed this picture of the structure this morning because we'd worked on the materials for a number of years before it was made evident that the initial structure that was determined was wrong. I mean, it was reactive, but where the sulfur was reacting with the polymer part was different than what was initially thought. But so now we have the right structure. So I thank the chemists for that. And this is work that was very highly collaborative with the Pyun group, and the Nyartsen group in chemistry was actually the Nyartsen group that really started studying and came to the realization that the structure that we've been using was incorrect. So we're happy for that. And this is you're not going to go into the details of how we make these. That we were working on again for about 10 years. It was somewhat serendipitous discovery to start with. Really just conversation between myself and Jeff Pyun, and I thought, oh geez, these might be good for. He thought they'd be good for high refractive index optics. I was concerned that they were orange because most of the high refractive index optics applications at the time were for things that would work in the visible, cameras, eyeglass lenses, things like that. They can't be orange, So I thought, what's the structure? And I saw all the sulfur. And I thought, gee, maybe the longer wave infrared transparency is pretty good, like better than ordinary polymers. So I got excited about that. You can see the refractive index is very high. I mean, ordinary polymers, you can see PMMA down here, polystyrene down here, and we're up here, and I'll show you even higher ones. And so we wanted to see though, are we really more transparent in these longer infrared wavelengths? So this is in the 3 micron region. So you're getting into thermal imaging kind of. Thermal imaging is really more focused in the long wave, around 8 to 12 microns. But you still have thermal aspects in the mid wave from 3 to 5 microns. these mid and long and near, these designations actually come from the atmosphere's absorption spectrum and what makes it through the atmosphere. So they go back to sort of atmospheric science. So this is a picture with a midwave camera that I have in my lab now. It was in Eustace Duraniak's lab at the time we took this, of a student behind a millimeter thick window of polymethyl methacrylate, which is plexiglass. And if you look really hard, you can see there's something there, really hard. And then we made a 1 millimeter thick window of our stuff, and boom, you can see everything. And so that was a key finding, and it got people excited that these materials would really be viable for mid-wave and long-wave infrared optics. And I think we learned pretty quickly that we weren't as transparent as the things that people were using, and that the cost benefits weren't significant enough to give up the performance that they had from things like germanium and chalcogenide. But we have continued to work on, and we made significant progress, and we're still working on that aspect of this, and we'll see a little bit. We could get even higher refractive indices by going to selenium. So sulfur selenium systems, mixed sulfur selenium systems have the advantage of being able to go to higher overall chalcogenide content without phase separation and other problems. So you can see, I'm gonna have to correct this structure too, I'm not sure. And we made Bragg mirrors. We made this is a classic dielectric type mirror. There's basically two main types of mirrors we use in photonics: metal mirrors and dielectric mirrors. This is a dielectric one, and you can see that all we need is basically for this is we need two different materials: a high index material and a low index material. This selenium system was a high index material. The low index material is actually, in this case, cellulose acetate. And we made mirrors. And the student who did all the spin coating, I was very impressed with her work. This was a number of layers, about 20 layers that you had to spin coat, using the process we use for lithography to make these coatings. And with a Bragg mirror, you can move the peak reflectivity around just by changing the thickness, which we showed very nicely here. And that was a nice early demonstration of the thin film capabilities of these materials. We also looked at the nonlinear properties. I promised a little bit about nonlinear stuff. And we did look at the nonlinear properties of these materials early on as well, using something called the Z-scan method. And in particular, they have pretty high nonlinearities. The selenium systems, so this is the sulfur-based systems, are about the same as silicon nitride, which is a moderately nonlinear material. And the selenium-based systems actually have an index of a nonlinear index that's almost as high as about as high as silicon, which is quite high, but also have low nonlinear absorption, which is an important consideration. And it all agrees well with a basic framework that we adopted from the early literature of nonlinear optics. I said we were making integrated photonics out of these, and we are. Student Abhinav Nishant, who's at Corning now, developed all of this with our instruments I showed you in optics, made thin films of this material. He learned how to etch very, very well to make these very, very smooth walls. Because you need those very, very smooth walls to keep the light from leaving. So we worked on devices. This is a device that splits the light into two pieces, usually equal. This is another device that does that in a different way. And this is one of those rings that I showed you before. And this is kind of the ring resonator is sort of a test device for a new integrated photonics technology. How good a ring resonator can you make? We do all kinds of things to design these. We simulate them. We look at simple waveguides to see what the output looks like. We do design of what the refractive index is inside the waveguide, called the effective index, and we characterize them, and we take, to tell how much light's going through in a somewhat accurate way, we take a waveguide and we look at how much light goes through, and then we cut it and we measure it again, and we cut it and we measure it again. And that's what this is called, a cutback measurement, to get an idea of how much light is lost in the waveguide. When you get these pretty pictures that simulate the light going in one side of this device and coming out two places on the other side. It's called a multi-mode interference coupler. This is a more standard Y coupler. This is the actual experimental data. It shows it's pretty darn good at cutting the light in half. And here we show a ring resonator that actually work quite well. This is simulation up top. This gap is, if we look at here, I have this little gap here between the ring and the waveguide. This is where the light actually couples from the multicolored stream to one color sitting on the ring. And here I've got that one color sitting on the ring, and this is looking at the sensitivity to that gap. So your lithography has to be able to control that gap size, in this case, from 600 nanometers to about 1100 nanometers, which is doable. And we got a nice, so this Q factor is a measure of how good your resonator is. And 64,000 is a good initial number. Silicon basically, I showed you earlier, lower Q factors. Silicon nitride, we have silicon nitride resonators, I'll show you in a minute, right, when I'm wrapping up, that have a Q of 2 million. So you can get very, very high Q resonators that are integrated photonic devices now. So this is a good initial number. Okay. In the spirit of some really new results that we've gone forward with these materials, which we call chips, both of these structures are accurate, as far as I know. And this is the structure I showed you before, and this is a different material. We developed this material to be more transparent in the long wave infrared. So you can see the difference organically here as I have aromatic system here, I have a completely aliphatic system here. Reducing the number of different types of bonds I have helps my infrared transparency. For a long time, the best polymer for infrared optics is polyethylene, because it's very simple. Carbon, hydrogen, that's it. There's no double bonds. It has very strong absorptions at some places like 3.3 microns, but big windows. So that was the spirit here. And it did work better than those systems. And what we've done here, and this is, and Dr. Kanjo Kim has been part of almost all this research I've talked about is here today. And, he really led a lot of the work on making these Fresnel lenses now. And a Fresnel lens was invented by Fresnel for lighthouses. Yes.
What did you just say? The increasing or decreasing the number of bonds does what?
Decreasing the number of different types of bonds creates windows of larger transparency windows in the infrared. So we got rid of double bonds. There's no double bonds in the system. So you got rid of anything associated with a carbon double bond, including the carbon hydrogen that is associated with a double bond. Yeah. So Fresnel lens was invented by Fresnel to make it easier to get lenses up to lighthouses. It's a flat lens, and you can buy Fresnel lenses made of acrylics, and you've probably seen demonstrations of melting concrete with sunlight with Fresnel lenses. You can make them really big. We like these because they're thin, and as I said, these don't really work as well as we initially hoped at these long wavelengths. But if we make things thin, not so bad. So Fresnel lens is a good choice. We developed this imaging system, and again, this is Dr. Kim and others, and we made our own target. We actually made this with a CO2 laser, so we could, because the Air Force target that people usually use is for the visible, and we're in long wave infrared, so we made bigger things. We made our own target. We call it the UAIR target, or UAIRT. And this paper is it literally went up a couple of weeks ago. Now it's not actually. It's the online version. The final journal version isn't ready yet. But our goal here was to show that we could image with this Fresnel lens better than we made progress over other things. And this gives you a feeling. This is a comparison of our initial systems. So these are the initial systems that we developed that have the aromatics. And you can see when you get to low temperatures, you really can't see much. This is a system that we have now, even at 30 degrees C, which is basically human body temperature, we can still image. Now we can't do as well as germanium yet. This is a germanium lens. You can see how good that looks. But this is, and we didn't show the PMMA here, but I mean, you can't get anything. It was kind of no point, because like if you had a PMMA lens, even at this thickness, you can't image anything. So this has progressed, and this is thermal imaging. This is imaging for sensing. This is actually a picture of a lens that has been developed by a company working on this for the near infrared. And you can see the high index actually does help. I mean, I can magnify things. This is the exact same size lens. This is a polymethyl lens. This is what the company calls polycalc lens. You can see that it has a much higher magnifying power and better light collection power, which is useful for things in 3D sensing, facial recognition, that sort of area. And I got a couple more slides, again, of new things. We have a new material that's different from these materials that I was talking about that use this, and didn't go into the chemistry, but it's a kind of a messy process. You melt sulfur together with the organic monomer, and there's only, you need to have the monomer be miscible in the sulfur, and there are only very few monomers that actually are. We're fortunate to have some that are actually quite well high performing. This is a different approach based on a sulfonyl chloride introduction to an organic monomer, and we're calling these also in the broad class of this inverse vulcanization reaction, but they're much easier to process. You can make big, these almost look like optical fiber preforms, and they have potential and actually work in the visible as well. So this is something that, if I talk in a couple of years, we have another paper we're about to come out on this with more optical devices in it, so that'll be coming. Okay, last couple slides, because I promised something about magneto-optics, and we are doing some interesting work in magneto-optics, and it's based on nanoparticles. Nanoparticles aren't good for everything, but some of you probably already have, or know people have quantum dot TVs. Quantum dots are the most successful nanoparticle technology probably at this point, and they allow you to make little particles of semiconductor that luminesce at different wavelengths. So that's an example of what, and they're generally in some kind of composite form. We're most interested in their composite form in polymers. I had hairy fiber earlier, now I have hairy cobalt nanoparticles. So the magneto-optic properties of cobalt and any kind of ferromagnetic or super paramagnetic system are very interesting, but I often have to work with some very fragile crystal to do that. So if you can make a nanoparticle and incorporate it into a polymer, maybe you can come up with a system that's easier to process. This is work in collaboration with the Pyun group again, where they've made nanoparticles of in the range of 15 to 30 nanometers in size. As you make the nanoparticle bigger, their magnetic properties improve, but they also have a tendency to cluster and block light. So this hairy ball, kind of afro haircut that it gets is there to protect it. And when we do that well, we get very high what are called Verde constants. This is an effect that was discovered by Faraday. It's called Faraday rotation. It was actually one of the effects that made Maxwell think about the relationship between the electrical and magnetic waves, because it was one of the first demonstrations that somehow magnetic field is something like to light, and the connection between electrical fields and light was understood at that point, but the relationship, it didn't make sense for them. It doesn't make, at that point, make sense that the magnetic field would be related to it. But if you apply a magnetic field in the direction of light propagation in any material, you will slightly rotate the polarization of the light. And that's called the Faraday effect. And again, was discovered by Faraday because he could make big electromagnetics and magnets in 1840, and that's about all you needed in a light source, polarized light source. So when you make these composites well, you can get very high Verde constants. This is actually a measurement of the rotation. Now, these are pretty thin samples, so we're talking about fractions of a degree rotations that we measured for these samples that we put in this system. But that if we take that and now we put that on a chip, then there's some interesting things we can do. So this is work that Dr. Shelby Jenkins did as part of her Ph.D., and now she's a postdoc in our group continuing some of this. But it's a very new idea of using a magnetic field to modulate light using a resonator. So the idea is I put light in one of these rings or other kind of resonators that interact with a certain wavelength of light. And initially, I get this kind of spectral response. When I apply the magnetic field, actually the spectral response gets worse, or you might say it gets worse. It changes, and it changes because the magnetic field is rotating the polarization. these ring and disc type devices are very polarization sensitive. So when they rotate, their spectral performance changes. So if you do this right, you can sit at some wavelength where initially, I've got a lot of power, and then I turn the magnetic field on. Now I've got much less power. So can I make a modulator that way? And we found out we actually could. These are actually chips, and we just got a fresh batch of these chips actually last week. So these are very high Q, high Q meaning very, very sharp peak resonators from a company called Ligantech in Switzerland, made of silicon nitride. And we actually packaged these in our packaging facility at Optics. And this was our initial data on these devices. And essentially, this is a wavelength situation. So way off of resonance, we didn't see any modulation. Right on resonance, right at the peak, we saw about 5 dB. So I told you 3 dB is about a factor of 2. That's about a factor of 4. So it's not great. It's not anything to really write home about from a modulator point of view, but it's a completely new way to make modulators using magneto-optically modified resonances in resonant integrated photonic devices. So I kind of did this pretty quickly, but all we do is we take these guys and we just take that nanoparticle composite. We actually take that top cladding off again. In the new resonators we just got, the company actually took the top silica off because these are all basically encased in silica. So we've got basically air clad. We just put the nanoparticle composite on top, and that gives us our magnetic field dependence that we want to make the modulation. Okay, so no lengthy concluding slide, just acknowledge some of the funders for this, and hopefully that was at least illuminating.
Unintended.
Thank you.
All right. Can you handle questions?
Absolutely. So
Okay,
if you
great.
have
Thank you,
questions
Bob.
online, just you can open up your microphone and ask the question. We can hear you in the room. Or if anybody in the room has a question.
The question is, what is the shelf life of the polymer in comparison to the silicon?
So shelf life can actually be very long. It depends on the polymer, so it depends on the conditions, though. I mean, if you're talking about just, I still have samples. I still have samples from our early work on infrared polymer optics. These orange materials that still look fine. They weren't waveguide. We weren't making waveguides at those times, but at room temperature, under kind of standard conditions, most of them are fine. But it's more, the real question is, what's the lifetime under some kind of more significant operating stress?
Actually, that was my next question.
Yeah.
So the thing with polymers is that they are not as stable as silicon. They work at a higher temperature. Their glassy transition temperature is generally lower, and sometimes they even interact with the environment like humidity.
Right, that's right. Yeah, so you have to look at what polymers bring you. So I can tell you that all the optics in your phone are polymers. Every single lens in your phone is a polymer, and the reason is there's the cost. They're so much cheaper to make, and at the same time, they're good enough under the conditions that are required there. So it really depends on what the application is as to how you can compete. You're never going to compete with, from a basic reliability point of view, you'll never. It's difficult for polymers to compete with glass, let's say, on the temperature side. On the chemical stability side, sometimes they're better, right? Polymers are acid resistant generally. The glass will dissolve. And from a mechanical point of view, polymers are also often better. One of the examples early on of polymer waveguide technology that we developed, and this was in my industry days. We had interconnects very similar to the ones that I showed you that were flying on aircraft for hundreds of thousands of hours with no failure. So you can do it. It's not. You can find systems that match your application in most cases, but you're right. In general, it's not something that you can ignore. You have to have that focus from the start what's the application and what are the requirements. You know, for one of the things that for, again, I mentioned it for the interconnect, one interconnect, and it's true of many things, is for more and more things, you have to survive a solder reflow. You know, so a solder reflow is pretty nasty condition. I mean, it's 260 degrees C for some period of time. So, you know, even some low temperature glasses have trouble with that. You know, so.
Do you see the temperature in the reflow of the maximum?
About 260. Yeah. Yeah, you know, you can look around. There's different protocols and people, you know, but generally it's around that. Other questions?
Oh yeah, I have a question. So when you use your polymer waveguides to connect chips, yeah, with the waveguide itself. So do you have reasonable losses there?
Yeah.
Losses?
Yeah. So that's a very good question. So the paper I put up, so we got on and off the two tips with about 6 dB of insertion loss, and which isn't bad. You know, I mean, we were pretty happy with that. I mean, in principle, we should have been able to do about 2 dB better. I mean, when we looked at the loss budget, we thought, okay, we should be able to do this at about 3 or 4 dB, and it was more like 6. But you know, it was encouraging that we could probably keep going that way. You know, so and the basic and most of that loss was in the coupling regions. You know, I mean, we looked at the propagation loss; it was about 1 dB, 1.5 dB, and it was really about 2 dB of coupling loss on the two sides. Yeah, so it's pretty good. It's pretty good, right? Yeah. So it gave us a feeling that okay, this could be a good way to go, and you know, but yeah, that's always, you know, it always has to care a lot about the loss, as you know. Other question?
Questions in the room? Do we have any questions online?
2 people left.
There was a slide that you had that was, we're showing the lenses, and I want to say it was called Capex. I didn't know what that, you said it had like a.
I had 2 lenses.
Yeah, exactly. That.
Yeah. What about it?
I don't know what that means, that Capex. I don't know what that means.
Oh, you know, I think you're talking about polycalc. Yeah. So there were or plexiglass. Is that what you're asking? I gave it a name.
You were comparing like what one had over the other, and
What was this? The higher magnification, right?
Okay.
The 2 lenses. Yeah. So the refractive index of the sulfur-based material is 1.7, and that of the plexiglass or polymethyl hydride was about 1.5. So just get for the same dimension lens, you get a higher magnification. Yeah, but that material is very related to these polymers I was talking about. Yeah.
I have a question. When you talked about nanoparticles,
Yeah.
Are you doing in-house synthesis?
Yeah, it's all in-house. Yeah. So basically the Pyun group got really good at making cobalt nanoparticles actually for magnetic storage applications a long time ago. So he had learned about that, and then when we came and said, hey, you know, we might be able to do some magneto-optic work together, we started doing that. But yeah, that's all here. Yeah. So if you're interested in any kind of magnetic nanoparticle, or you know, other nanoparticles as well, you might want to contact, you know, Dr. Pyun. Yeah. Okay. All right. Well, thank you very much.
Bob, thank you so much. Everybody in the room knows we have been recording this presentation, so if you'd like to revisit it, we'll post it online, and Bob will send you a copy as well, so you have that.
Thank you.
And then in the spring, we are going to be hosting more of our recess sessions, so please keep an eye out on energy.edu, arizona.edu. Yeah, great.
Thank you.
Appreciate you all joining us today.
Thank you. Thanks for your attention.